But we're also going to do a short little thing on average rate of change because we need to learn it at some point in this unit, and I think we were supposed to do it earlier, but we forgot when it was supposed to be, and then it's on tonight's homework, so we figured we'll just teach it today. It's really short though. So, absolute extrema. We'll start with that. And we'll just look at an example first here. So we're looking for the absolute maximum value of f of x on this interval. It's the same function that we did in the warm-up. I did that on purpose since we already kind of did a lot of work for it. Delta math refers to this as a global maximum. I'll usually call it an absolute maximum, but that's what delta math calls it. And notice it's on an interval here. So we need to find the biggest y coordinate. When we do questions like this, it's always on an interval. So last year in pre-calculus, often you're looking at graphs and like pointing out the absolute max or min. In calculus, it's always going to be on an interval. So we already did a lot of work for this, so let's just copy it over. And so we said x equals 1/2 and -1. And we know that there is a local max at, was it 1/2? Is that right? And a local min at 1. Or no, sorry. Other way around. -1 and local minimum at x equals 1/2. So, what could possibly be happening in this graph? We're just going to do a couple options here. So our interval is from -2 to 1. So here's -2 and here's 1. And we know we have a maximum here at -1, and we know we have a minimum here at 1/2. And so what could be happening here is the graph could come up, here's our maximum, and then we go down, and here's our minimum, and then the interval ends there. Or it could look something like this. And I'm just making up y coordinates here because we didn't find any y coordinates. It could look something like this, where we have, they come here, here's our maximum, there's our minimum, and then it ends like there. So just based on what we know already, it could be one of these two situations. Turn to your neighbor. If we're looking for an absolute maximum, what's the difference between these two situations here? Talk about it.
So the one on the left isn't possible.
It is possible. Yes, these are the two possibilities. These are two of the possibilities.
Isn't that a bounce?
I mean, you know, it could go like this. It doesn't matter.
Yeah.
We're looking for the maximum. Okay, so in terms of the absolute maximum, what's the difference between these two graphs? Yes, the absolute maximums are different in the two graphs. In the one on the left, the absolute maximum is the same as the local max. But in this one here, actually the end point of the graph, you know, we could imagine it keeps going up like that. But where we cut off this interval is actually higher than the local maximum that we have. And so the absolute max is one of the endpoints. Now, how will we know which situation we have? What do we need to do? Sarah? Exactly. We just need to plug in the endpoints. Now, based on what we know about this function already, because we did the derivative and found the local extrema here, do I need to plug in both endpoints, or do I just need to plug in one? David? Why just one?
Well, actually, at least what you drew, that's the only one that's.
Yeah. From what I drew, for sure. Yeah.
Because it's negative on the left side.
It's
It's positive.
what went negative to positive?
From the sign chart,
Mm-hmm.
it was going from negative to positive there. So.
At -1.
I named one.
Yes, the sign chart has to do with it. So what's happening to the left of -1? What's the function doing? Increasing. So that means whatever comes before -1 is going to be smaller than the value that we have at -1. It's only increasing there. There's no way, if the function's increasing for this region right here, there's no way that we could somehow have a point up here that's actually higher than the local maximum, right? Because then this would mean that it had to decrease first. But we know the function's not decreasing over there. It's just increasing. So in this case here, yeah, we only need to plug in -1 and 1 because we know that there's a local maximum. So that could be the absolute maximum. But the only other possibility is that the endpoint is the absolute maximum because our function is growing here. So whatever value is there at 1 is going to be higher. Now, we won't always know this. We won't always do a sign chart beforehand. That'll be the next example. But right now in this example, all we need to do is plug in -1 and 1. And what we're doing right here is called a candidates test. And usually our candidates are going to be the endpoints and the local extrema. So x equals -2 is not a candidate this time because f of x is increasing up until -1. Or we could say because x equals -1 has a local maximum. And x equals 1/2 is not a candidate because why? It's a minimum, yeah. But normally, our candidates are both endpoints and all extrema. We just happen to know more information about this function ahead of time. Okay, so go ahead and plug in -1 and 1 into f of x, and let's see what we get. Okay. Okay. Any questions on that? Yeah.
If you ask us to find like the local maximum, or you know, like normal question, do we have to put local in our justification, or if we don't, would it be wrong?
That is a good question. Yes, it would be wrong. So we do want to make sure that when we're finding local or relative extrema, that we do call them local or relative extrema because there are two types of maximums and two types of minimums. Yes. So yeah, we will have to be specific with that. Okay, so we'll do another example of that. Okay, so for our first step here, just find the zeros of f prime of x. Don't do a number line test. I'll explain why once we get there. X.
What?
Okay, did I factor this right? No?
-2 or -2.
Oh, minus 2? Oh, yeah. Okay, so we get x equals 0, 2, and 4. Okay, we, instead of doing a number line test, we could do a number line test and determine which of these are minimums and maximums, and that would give us a little bit more information. Usually if we're looking for an absolute max or min, it's going to be faster just to put all the zeros and the endpoints into our table of values, because those are all our candidates, and just plug those in and see what happens. Now, we actually don't need to plug in all the candidates. Which one is not a candidate here? 0, yeah, it's outside the interval. So we want to just do 1, 2, 4, and 5. And usually this is our fastest way, rather than doing a number line test. So go ahead and plug those in, and let's see what we get for the absolute max and min. Okay, so I got 6, 13, -3, and 22 for my values there. A lot of these numbers got really big, but they were canceling out, which is kind of nice. Like on the last one, like 625 plus 400 is 1,025, minus 1,000 is 25, minus 3 is 22. So it was working out nicely. Okay, so from here, the absolute maximum is what? 22, and the absolute minimum is -3. Yes. So remember, the answer is the y coordinate for these. So we say what the maximum is, we list the y coordinate, and then we say where it is. So that's how we answer those.
On the test, can we just say like abs and max?
Yeah, you can abbreviate, yes. As long as it's clear, you know, you can't be like the absolute max of f of x is 22, you know. You can't do anything like that.
Do we have to say like the absolute maximum on the interval, like 1 to 5?
Yes, we do. Yes. There we go. Yes, thank you. I forgot about that. Sometimes questions will just ask like, what is the absolute maximum? And you could just answer 22 as your answer. Okay. So that's absolute maxes and mins. Slightly different than relative maxes and mins. Again, normally when we set the derivative equal to 0 and find the possible local extrema, just plug them into the function along with the endpoints and see what the biggest and smallest y values are. That's normally our process. On the first example we had more information to work with, and so we were able to use that to shorten our process, but that's the idea. Any other questions? Okay. We're gonna do average rate of change. So the average rate of change is the slope of the secant line on some interval. We'll call it AB. So if I just do a little graph right there, like, it would just be the slope of that line.
Wait, what is a secant?
A secant line is a line that intersects a curve at least 2 points. And so throwback to geometry. All kinds of geometry comes back in calculus. It's really great. We have a tangent line, of course, and we have a secant line. And we learned about those in the circles unit. So, and we talk about both of those in calculus. So this is our average rate of change, which we do often abbreviate. You can abbreviate AROC, which sounds cool. But then if I had a tangent line, let's say like right there, what kind of rate of change does that tell us? Slope of the tangent line tells us what kind of rate of change. Rate of change at one point, what's the word? Instantaneous rate of change, yeah. Instantaneous rate of change. Or we abbreviate that IROC. There's a theorem actually that we'll look at later in the year that talks about finding places where they're the same thing, but we're just learning average rate of change for now. Average rate of change, to calculate it, is just going to equal f of b minus f of a over b minus a. And turn to your neighbor, what is that? Okay, so yeah, that is just the slope formula. So we just do y minus y over x minus x. So average rate of change is nice and easy. So let's do an example here. Okay, so do this one with your neighbor. Hopefully you know some things about this one already. Okay, so let me just show you guys how you want to make sure that you write this. You want to make sure that you either say like f of 5 equals, what was f of 5 again? 22, right? And f of 1 was 6. Okay, so we know this from the last problem. So either clearly label those, and then so you're doing like 22 minus 6 over 5 minus 1. Or, so either write it that way, or write f of 5 minus f of 1 over 5 minus 1, and then say that equals 22 minus 6 over 5 minus 1. So just make sure that you're clearly indicating where these numbers are coming from. So that's just the only thing to be on the lookout for. I usually do it this way, but you know, whichever way you want to do it. So 22 minus 6 is something. Yeah.
Will we get points off if we wrote after 1 equals 6, after 5 equals 22, and then did the mental math and did like just the answer? Is that?
Usually on the AP exam, they want to see like this, something like that to show the setup. Yeah. Yeah. You usually get a point for like demonstrating that. Yeah. So I would say just go ahead and show it. Yeah. What is 22 minus 6? My brain's not working. So 16. 16 divided by 4 is 4. The average rate of change is 4, right? Okay, great. Okie doke. That is average rate of change in
Just
absolute
write
extrema.
equals 4, you write average rate of change equals 4.
There you go. Often, so most of the explanations and the writing and the wording that we do are practicing for future free response questions. So usually in a free response question, it won't be asking us to find the average rate of change. It will say something like, when is the average rate of change equal to the instantaneous rate of change? And so you wouldn't need to write this sentence. You would need to show this work, and then you would need to show like setting the derivative equal to 4. That's how we would do it. I'm giving you guys spoilers for February right now. It's just crazy. Normally I don't do that, but you would show those things setting equal, and then you would say it happens at t equals whatever. So you rarely will have to write a sentence like this specifically, but that's the idea. Okay, cool.